Welcome back to the Now You Know channel, and let's get into intermediates and their stability. So imagine a molecule in the middle of a reaction, caught in a high energy state like a climber halfway up a cliff. These are intermediates: carbocations, carbanions, carbenes, and free radicals, and their stability decides the reaction's fate. In this video, we are diving deep into their structures and what makes them stable, and how to rank them. With practice problems to test your skills, let's stabilize those intermediates. So starting off, what are intermediates? Intermediates, well, they are high energy, unstable, reaction species that are generally produced and consumed during a reaction. And when it comes to intermediates, we have four that are the most common and ultimately what we deal with. We call these the big four intermediates. And they consist of carbocations, which we denote as C with this little plus up in the corner. You can circle it or not. And these are positively charged carbons. We have carbanions, which are denoted as just a C minus, which you can circle. And it is known as negatively charged carbons. Third, we have free radicals, which are neutral carbons with an unpaired electron. And we have carbenes, which are uncharged reactive intermediates. And there's more to come about all these big four in this video. So the biggest thing is stability. Now stability is going to determine how easily the big four form and survive. Let's move this down. So what determines stability? Stability has three key factors. One, resonance, which is the movement / delocalization of electrons, which there is a whole nother video on that. Feel free to go pursue that. Two, sigma bonds, sigma bond donation, which is also known as single bond donation. Three, inductive effects, which is electron donation or withdrawal. Let's just continue down here. Withdrawal via bonds. So this is what determines our stability. And you're gonna evaluate which characteristics are in each molecule, and from that go down stability. So let's jump into our next topic, which is stability of carbocations. Okay, so carbocations are electron deficient. So this is missing a pair of electrons. So stability comes from electron donation. Some carbon bearing a positive charge, which we do denote as a C+. And it usually has only 6 electrons in its valence shell. So let's kind of draw this out. So this can be seen as, I'm going to do this in kind of 3D form. So here's your carbon. It's in a trigonal planar formation. And we have this open p orbital, which is empty. We have an empty p orbital. And ultimately, this has a positive charge on it. And so this is what they're going to look like. They're going to be a trigonal planar just like this. And you're going to have this empty p orbital, which allows for reaction to happen because basically you're open. And let's go into the order of stability for carbocations. And first off, let's understand that carbocations are stabilized by electron donating groups and resonance. Let's start this down here, resonance. Let's just move this all around. So the order of stability is going to go as follows. You're going to have benzylic carbocations. This is a benzylic. You're going to have allylic. These two are where your resonance come into effect to stabilize your carbocations. You're also going to have a tertiary carbocation. And these are all going to be more stable than a secondary carbocation. Which are all more stable than a primary carbocation. Which ultimately is more stable than a methyl carbocation. And this is how stability goes. Where the methyl being least stable. And the benzylic, allylic, and tertiary being the most stable. Okay, and let's look at why this happens right here. So let's look at this here, tertiary carbocation. And notice that you have this lack of electrons. And in this situation, this carbon here is going to donate electron density, just like this. And when they donate electron density, it works to stabilize this carbocation. So that's why a tertiary carbocation is more stable than a secondary, because in this tertiary carbocation, you have 1, 2, 3 donating groups, 3 carbons donating electron density, while on your secondary, you only have 2 groups donating electron density. And so on and so on, it falls off, right? You only have 1 group donating electron density in your primary carbocation. Let's move on to the next big intermediate, and that's stability of carbocations, carbanions, my apologies. And carbanions have a negatively charged carbon atom. It is electron rich, making it a good nucleophile, which will come into play as you get deeper and deeper into organic chemistry and chemistry. Another note, carbanions are nucleophilic and basic. And let's draw out what these kind of look like. So you're gonna have your central carbon, right? And then you're gonna have, let's have a hydrogen going back. Let's have one coming into the plane, and let's have one coming forward. And these are going to be hydrogens. And you have this extra one in the plane right here, and there's your pair of electrons. They're commonly denoted as such. With your negative charge here and here. And this would be a methyl anion. So let's move on to the order of stability for this. Notice that the order of stability is going to be your opposite of carbocations. So carbocations were stabilized by more substitution on that charged carbon. In this case, it's going to be reverse. So your tertiary carbanion is going to be less stable than your secondary carbanion, which is going to be less stable than your primary carbanion, just fill that in, which is going to be less stable than your methyl carbanion. And I want you to also notice that your benzylic and your allylic is also very stable. And this is because resonance is always a huge stabilizer. It delocalizes those electrons, which does a tremendous job in stabilizing. So whenever you see resonance, always think stability. Always think most stable and how that is playing a role. And so going from, in this case, left to right, being for our stability, where left is our least stable and right is our most stable. All right, our next is going to be stability of free radicals. So free radicals are electron deficient because they lack an octet. Remember the golden rule, every atom wants 8 electrons in its valence shell, and that's not including boron and hydrogen, of course, but every other atom wants an octet. And overall, free radicals are neutral, so no formal charge. And what these are going to look like is going to be like something as such, where you have these 3 groups and you have just a radical. Let's draw this in 3D for you. And you're going to have this p orbital with just 1 unpaired electron in it. Like carbocations, radicals are stabilized by the electron donating effect of alkyl groups, which are just carbon groups, right? So if carbon next to a carbon, that's an alkyl group. So the order of stability for free radicals is going to be the same as carbocations. So you have your benzylic. There's your little radical right there, just denoted as a dot. Benzylic. You have your allylic. You have your tertiary radical. You have your secondary radical. And you have your primary radical. And lastly, of course, a methyl radical. Secondary, primary, and methyl. And stability from, in this case, is going right to left, where your methyl is your least stable and your benzylic, allylic, and tertiary are going to be your most stable in terms of free radical. Okay. The last big intermediate is carbenes. And what are carbenes? Well, carbenes are uncharged reactive intermediates. This is what they're going to look like. You're going to have your carbon, and you're going to have, say, hydrogens. There's going to be any R group, right? That's how you denote that. You're going to have a pair of electrons. This is known as methylene. Something important to note, that this is going to be a sp2 hybridization. So this is really what it's going to look like. This is highly reactive, and it's created during the course of the reaction, also known as in situ. Like I said before, it's very reactive. It has both a pair of electrons and an empty p orbital. And this double situation of a pair of electrons and empty p orbital is why it's so reactive. And this means it also can react as a nucleophile or as an electrophile. And again, if you're freaking out because you don't know what that means, don't worry. There's more to come on that, and it's just going to be helpful during your synthesis and mechanisms which are to come. Some other things to note is there's no order of stability for carbenes. And this is because there's no difference all are very reactive. This is how I think of it. Carbenes don't like being carbenes. So they will react very fast to change. So now let's jump into some practice. In this case, it is rank the carbocations from greatest to least stable. So I challenge you to pause this video, review your notes, and try this before I answer it right now for you. Okay, and let's jump right into it. So let's look at A. So when we look at A, we're going to notice that our carbocations right here on this carbon. So let's look at everything attached to this carbon. And the only thing attached to this carbon is another carbon right here. That's it. There's no resonance denoted by, which we would know because there would be either a double bond or a pair of electrons. And that's it. All there is another carbon. So we can label this as a primary carbocation. Now let's look at B. B, we notice that the carbocation is going to be this carbon right here. So what's connected to this carbon? Well, we have this carbon connected and this carbon connected. There's no resonance, which we would know if there was a pi bond or a double bond or a pair of electrons. So we can label this as a secondary carbocation, which I'm going to shorthand as such. Let's move on to C. C, we notice that this carbon is our carbocation. We don't see any resonance, which we would know, again, by a double bond or unpaired electrons or paired electrons. So what's connected to this carbocation? Well, we got 1 carbon, 2 carbon, 3 carbon. So this makes it a tertiary carbocation. And now D. Let's look at D. We have this carbon being our carbocation. We also see that we have resonance. And where's this resonance? Well, this resonance is from this double bond. So let's look at this a little bit more. Let's do this resonance structure. And when we do this resonance structure, we see this happen. I'm gonna use this pink to show the movement. We see this bond move here. And when we see this bond move there, we see this turn into our carbocation. Ultimately, this is resonance, which brings up stability, right? We see resonance in this case. And this is allylic, right? You don't have a full benzene ring. You only have one. You only have a double bond right next to your carbocation. So making this allylic. Which always bumps us up. And we also see allylic tertiary and allylic secondary. If you don't know how to do resonance and resonance structures, don't worry. I have another video on that you can watch to get you caught up on that. So I'm going to denote this as allylic tertiary, just because this helps in the stability. And let's write out the stability. So in this case, allylic is more stable, is the most stable, because you got resonance. Resonance is automatically going to jump it up to one of the most stables. So you got your D. What's next? Well, if you look at A, B, and C, you notice that there's no resonance, so we don't have to worry about that. So the only thing to worry about is whether it's tertiary, secondary, or primary. Well, we know that with carbocations, tertiary is more stable than secondary, which is more stable than primary. So since we have tertiary, secondary, and primary, we can just go down the row like that. So we have C is the next in stability, which is more stable than B, which is more stable than A. And there you go. There's the stability of these carbocations. Let's move on to the next one. The next one is rank the following radicals in order of stability. So let's do it the same way. We know is that this carbon right here is where your radical is sitting upon. We don't see no double bonds or pairs of electrons. So let's move on and see how many carbons are connected to it. And we have 1. So this is a primary radical. Let's move on to the next one. We notice our radical is on this carbon. This molecule altogether has no resonance, which we notice because there's no double bonds or pairs of electrons. So let's look at what it's connected to. It's connected to 2 carbons, so this makes it a secondary radical. Let's move on to the next one. We realize that the radical is right here on this carbon. Connected to it is 1, 2, 3 carbons. So we can denote this as a tertiary radical. Let's move on to D. The radical is right here. We have resonance, which is right there, right, with that double bond. So let's go ahead and do that resonance structure. You don't need to. As long as you know that it has resonance, it helps you. But we can do this resonance structure, which I'm going to show the resonance via as such. Again, if you don't know how to do resonance structures, don't worry. I have another video on that you can watch and get up to speed. Anyways, Since this isn't a full benzene ring, right? Because in here you don't have all your benzenes. It's allylic. Oh, let's change back to that color. It's allylic. And we're just going to go with the first one because it helps, and it's going to be connected to 3, so it's allylic tertiary. Well, we know that radicals have the same stability as carbocations, so let's go ahead and rank those. And allylic is first, right? Resonance is always a dominant stabilizer, so we bring in allylic first. So our stability. Next, we got our tertiary, which is C. Next, which would be our secondary, which is B. And of course, lastly, which would be our primary radical, which would be A. Let's move on to another one. This one's getting a little bit more tricky. I challenge you to pause the video, go ahead and try this one, and then unpause it and see if your answer is correct. See if you analyzed it the right way. Okay, so let's start into this. We see resonance on A, right? We have a double bond. Whenever we're breaking these down, let's always look for pairs of electrons or double bonds, because this instantly makes us think of resonance, especially when you have both. If you have both in the same structure, you most likely have resonance. Of course, there's a little bit extra nuances to resonance, which you can watch that video to understand. So let's show this resonant structure. You have these electrons move here to form a double bond, and these of the double bond move here, forming this structure. So ultimately, we know this is allylic, right? We don't see that benzene ring. I'm going to say, in this case, we got to think, okay, what is this? This is a negative sign, so this is a carbanion. Carbanions have opposite stability of carbocations, so the more substituted, the less stable, right? But as you remember, resonance always stabilizes. It's always a predominant stabilizer. So in this case, we can look at B, C, and D and realize there is no resonance. So therefore, this allylic is all we need to know. Let's look at B. We see that right here is our carbanion. There's no resonance, right? So let's see what it's connected to. It's connected to 2. This is going to be a secondary carbanion. Let's look at C. C has no resonance, but we see it's connected to, it's bonded to 3 carbons, so this makes it a tertiary carbanion. Let's look at D. Right here is our carbanion, and there's no resonance, right? There's no double bonds or pairs of electrons. So it's bonded to 1 carbon, making this a primary carbanion. And let's rank the stability. In this case, resonance, right? So A is going to take over, is going to be our most stable. Then carbanions. The more substituted that carbanion is, the less stable it is. So in this case, our primary carbanion is going to be next, followed by our secondary, which is B, and lastly our tertiary, which is C. So once again, let's look into this. Let's just break this down a little bit. A is our most stable because it's allylic. It has resonance, which ultimately is a more dominant stabilizer. Then we have D. D is next in stability because the carbanion is only connected to one other carbon, making it a primary carbanion. It being a primary carbanion, that means it is the next most stable, as the more substitution on a carbanion actually decreases stability, because of what happens is those other groups donate electron density to that carbanion, which makes too much negative charge on that carbanion. And then B is our next, because B is a secondary carbanion, which means this carbon is going to donate and this carbon is going to donate electron density, which is making it less stable than D, right, where D only one donates carbon or electron density. And ultimately C, you have this carbon donating electron density, that carbon donating electron density, and that carbon donating electron density. And when all those donate electron density, it just overwhelms that one carbon and makes it less stable. So our stability goes A, D, B, and C. Let's do it again. Rank stability of these intermediates. This is a little bit more tricky. Here, let's identify it. Right here is our carbocation. There's no resonance, but there is two bonds, right? It makes two bonds. And so this is a secondary carbocation. Here, this is our radical. Notice that we do have resonance, right? So we can name this allylic. Oh, sorry, wrong color. We can name this an allylic primary radical. Next, we have a carbanion right here. Let me draw in these natives. Carbanion. This one has no resonance, so we don't have to worry about that. But it is made to three. It has three bonds to other carbon groups, making this a tertiary carbanion. And now let's look at D. D has no resonance. It's a carbocation. The carbocation is right here. Has no resonance, but so this carbocation is a primary carbocation. So when we rank the stability, this is what we need to think. Okay. We're gonna look at these. We're gonna look for resonance. In this case, there's only one with resonance, and that's B. Okay. B is a allylic radical. Resonance is a dominant stabilizer. Let's go next. Would be next. Let's go A. A. If you look at it, it is a cation. It is secondary stabilized, so it is stabilizing. It's being stabilized. Let's look at D. Or actually, let's look at C. If we look at C, we have a tertiary carbanion. What we know about carbanions, we know that the more stabilized they are, the less stable they act. The more substituted they are, the less stable they actually are. So in this case, this isn't stable. This is actually at its the most unwanted state. It doesn't want to be in this situation, right? And let's look at D. And D is a primary carbocation. So if we had to rank these, let's do the stability. Well, the first one is easy. It's B, right? Because it has resonance. Resonance automatically is the dominant. Next, it would be A. because it's actively being stabilized, right? It's at one of its most stable forms, which is where A is at. Next would be D, because it's actively being stabilized, right? And then last would be C, because a carbanion in this state is so unstable that it actually makes D more stable than it. So in this case, C would actually be last, which makes sense, right? So let's move on to a little review. So let's just recap what's going on. We have carbocations. Let's look at their order stability. You have resonance and tertiary. Then you have secondary, primary, and then you have your methyl, right? Properties of a carbocation is it's electrophile. So it's electrophilic. And it's also a strong acid. Next, we have a radical, right? So this is what radicals. Their stability is the same as carbocations. So we have resonance and tertiary. We have secondary. Let me clean up that 2 for you. Secondary, primary, and you have a methyl radical. These are electron deficient. Next, we're going to have carbanions. And their order of stability, you're going to have your resonance. And you're going to have your methyl carbanion. Followed by primary, secondary, and tertiary. And carbanions are nucleophilic. And strong bases. Last, we have carbenes. Which have no order of stability because they're just so unstable. And for properties, they are both, change that color, they're both nucleophilic and electrophilic. So I challenge you to try ranking the following based on stability. Go ahead and drop your answer in the comments. Don't forget to like, subscribe, and hit the bell for more lessons and videos that are coming out soon. Thank you for watching Now You Know. I hope this is helpful, and stay tuned for more.